Hello everyone, today I'm going to teach about Isothermal Reactor Design. Okay, the objectives of our chapter is for sizing batch and semi-batch reactors, CSTR, PFR and PBR for isothermal operation given the rate law and also the feed conditions. And then we can use KRD algorithm in solving chemical reaction engineering problems. Okay, there are 5 solution algorithms for isothermal reactor, which is, I'm going to write it at the whiteboard. Number 1, mole balance. Number 2, rate law. Three, stoichiometry. Four, combine. And 5, evaluate. Alright. Okay. So we're going to use these 5 steps. Okay, first of all, the scale up of liquid phase batch reactor data to the design of CSTR. Okay, we can use these 5 steps to obtain the K. First step, mole balance. As you can see, mole balance for batch reactor is Na0 dx over dt equals to negative Ra V0. The next step is rate law, which is negative Ra equals to KCS squared. Next slide. And then the third step is stoichiometry, which is Ca equals to Cn0 in bracket 1 minus x. And then we combine, it becomes negative dx over dt equals to Kcn0 1 minus x squared. And then lastly, we evaluate and get the reaction time Tr equals to negative 1 over Kcn0 dx over 1 minus x squared equals to 1 over, lastly we get 1 over Kcn0 in bracket x over 1 minus x. And then we plot the data of 1 over Cn0 x 1 minus x over time. We get a linear plot. And then similarly for first order reaction, you can try it yourself and get the y-axis ln Cn0 over Ca, and then we get the slope 1 over k. The total cycle time for batch reactor is usually longer than the total reaction time. Typical cycle time is given below. As you can see, for the charge feed reactor and agitate, TF is from 1.5 to 3 hours. Next, the heat to reaction temperature T is 0.2 to 2 hours. Number 3, the carry out reaction TR, it can varies. And then number 4, anti reactor, it varies from 0.5 to 1 hour. The total cycle time is 3 to 6 hours. This example, you can try it by yourself. Next, let us move to the design of CSTR. Okay, let us recap for single reactor. For design equation for CSTR, V equals to Fn0 minus Fa over negative Ra, which is equals to Fn0x over negative Ra. And then the constant volume system, V equals to V0. So the equation we get V equals to V0 in bracket Cn0 minus Ca over negative Ra, where Fn0 is equals to Cn0 V0. Please remember that. And then in terms of space-time, tau equals to V over V0, which is equals to Cn0 minus Ca over negative Ra. And incorporate negative Ra equals to Kca. We change it into tau. We get tau equals to Cn0 minus Ca over Kca, which is Ca equals to Cn0 over 1 plus tau k. Lastly, for Cn0 equals to Cn0 in bracket 1 minus x, we get x equals to tau k over 1 plus tau k. And then for Damcommler number is for CSTR. Please remember that. And then we can give quick, the uses of dump collar number is, it gives quick estimate on the degree of conversation in reactor, which is equals to negative R N naught V over F N naught. If the dump collar number is less than 0.1, then X is less than 0.1. But if the dump collar number is more than 10, then X is more than 0.9. For first order reaction, the dump collar number is tau K, but for the second order reaction, the dump collar number is tau K Cn0. Okay. This is the example of design of CSTR in series. As you can see, the reactor is arranged in series. For first order reaction with no volume change. So the volume is constant. The volume is there is no volume change throughout the reaction. Okay, the design of CSTR in series just now. The concentration of A is Ca1 equals to Cn0 1 plus tau 1 over K1. Previous slides. As you can see there, Ca1. Okay, next. And then for reactor 2, which is the exit one, we get Ca2 equals to Ca1 over 1 plus tau 2 K2 equals to Cn0 in bracket 1 plus tau 2 K2 times 1 plus tau 1 K1. Therefore, for n reactor in series, we get Cn0 equals to Cn0 over 1 plus tau K to the power of n. And then the X is equals to 1 minus 1 over 1 plus tau K to the power of n. Okay, finish, that's all.
Alright students, so I will explain to you about the design of CSTR in parallel. Okay, for the design of CSTR, which is the CSTR in parallel, we assume that both reactors have a same size, and then we assume both have similar operating temperature and feed rate. Next is identical feed rate, size and temperature. Therefore, x1 equal to x2 and equal to xn equal to x, and negative RA equal to negative RA2 then equal to negative RAN. And for the volume of individual reactor, Vi is equal to V over N. For the molar flow rate, FA0I equal to FA0N, which is F is the flow rate of the reactor. And from the individual reactor, volume Vi equal to Fa0I in the bracket Xi over negative RAI, and then we get the final equation, which is V equal to Fa0X over negative RA, which is the mole balance of CSTR. Okay, next slide. Right, for the tubular reactor, usually used for gas phase reaction, and then assume plug flow behavior with no pressure drop and no heat exchange with the surrounding. So imagine this is plug flow reactor, and there is no we assume that no radial variations in the velocity, concentration, temperature or reaction rate. And in the equation for differential form, Fa0 dxa over dV equal to negative RA, and the integral form V equal to Fa0 integral of dx over negative RA. Next. Okay, just now we see for the gas phase reaction, so now is liquid phase reaction, and it is second order. So we have to follow the 5 steps mentioned earlier by previous video. First step is mole balance. For the BFR, dx over dV equal to negative RA over Fa0. And then for the rate law, negative RA equal to KCA square. And third step, stoichiometry, Ca equal to Ca0 in the bracket 1 minus x. And we combine the stoichiometry, dx over dV, KCA square over Fa0. And then we solve for the equation and evaluate V equal to V0 over KCA0 in the bracket x over 1 minus x. But in terms of dark column number, we can use x within the conversion equal to dA dark column number over 1 plus dark column number. Alright, moving to the next slide. Gas phase reaction. If the temperature and the pressure is constant, Ca is given by Ca equal to Ca0 in bracket 1 minus x over 1 plus epsilon x. Epsilon is actually the expansion factor, and we're gonna explain after this. Next is for second order reaction, volume is equal to Fa naught over Kc A naught square, and integrate of in bracket 1 plus epsilon x square over 1 minus x in the bracket square. Alright, this how does volume change affect the conversion? So, according to the graph, conversion against volume, this is for A is changed into B over 2, the stoichiometric value, and epsilon is equal to negative 0.5. So, as you can see, B is 1 over 2 is equal to negative 0.5. It is negative because it is reacted. Second is A and goes to B, 1 to 1, so the expansion factor is 0. And the third one is A is reacted to B, and the epsilon is equal to 1. And we know our Kc N is equal to 2 m3. So, next slide. For the pressure drop in reactors, use differential form of the mole balance equation in terms of catalyst weight. So this is the equation for you to calculate the pressure drop in reactors. Alright, next. Okay, for example, this reaction, which is 2A goes to B plus C, then rate law is equal to negative RA equal to KCA square, which is because the A have a stoichiometric value is 2, and then stoichiometric gas phase reaction, we have the formula of Ca equal to Ca naught and bracket 1 minus x over 1 plus epsilon x and times with P over P naught and P naught over T. And you must remember the formula here is important for the combined operation, which is Fa naught ds over Tv equal to K in bracket Ca naught 1 minus x 1 plus over 1 plus epsilon x squared, and then P over P naught squared. So next. So this is for isothermal operation, the overall equation we get from previous slide. So this need to know P over P naught because it is equal to catalyst weight per volume. Okay, next. Alright, for the eigen equation, we got the differential of pressure dP over dz over dz equal to negative G over rho Gc dP, and in bracket 1 minus V over V cube, and another bracket 150 1 minus V micro, then over dP plus 1.75 G. It depends whether it is laminar or turbulent. If it's laminar, then we take the laminar only, and the turbulent, the turbulent. So next is variable gas density, rho equal to rho naught, rho over rho naught, then multiply by T naught over T, then multiply by flow rate, Ft naught over Ft. And we combine the both equation, we get dP over dz equal to negative G over rho naught Gc dP, and then the bracket 1 minus V equal to the top one, and just multiply with the gas density. Alright, and then the last equation, we get dP over dz equal to delta naught multiplied by pressure, temperature, and flow rate. Alright, next. Alright, the weight of the catalyst in terms of distance z down to the reactor. So the volume weight is equal to, in the bracket 1 minus V multiplied by the area AC, then Z, then rho C. And then we differentiate the W, the equation above, we get 1 minus V AC, rho C, dz, Then we combine dP over dV, we get negative beta naught over AC in the bracket 1 minus V, and then PC multiplied by the gas density, and then simplify, we get the dP over the dW equal to negative alpha over 2 T over T naught multiplied by P naught over P over P naught, then multiplied by the FT naught. Next. Then we assume for the 1 P over P naught, y is equal to P over P naught. To simplify the equation, we assume y equal to P over P naught, we get dy over dW equal to negative alpha over 2y, then multiply with P over P naught and Ft over Ft naught. Next is this is from the mole balance Ft, similar with the mole balance Ft equal to Ft naught plus Fa naught delta x, and epsilon equal to Ya naught delta, also equal to Fa naught of Ft naught delta. And then after we derive, you get dy over dV equal to negative alpha over 2y P over P naught and 1 plus epsilon x. Okay, the question is how pressure drop affects the reaction. So it affects with the rate law, the epsilon, and also concentration. So the first one is the epsilon value is 0 and P is equal to P naught 1 minus alpha W to the power of 1 over 2. So the graph we get the graph will slightly decrease, and then for the second graph we calculate the concentration Ca equal to Ca naught, but multiply with P over P naught, then the graph will slightly decrease, and then the third one also the same. But the fourth one is the graph will increase because there is no pressure drop. Yes. Alright, next. Okay, that's all for tubular reactor. So students, if you have any problem regarding this chapter, you can email me anytime. I will reply to you as soon as I can. Okay.